Amazon Web Services, which is AWS, as you know, based in San Francisco. They have AWS also has probably offices in Silicon Valley here in Mountain View, I presume. He's a co-author of O'Reilly book. You probably know O'Reilly is a very famous publisher of books and organizers of conferences. His book is Data Science on AWS. He's the founder of many global meetups focused on Apache, Spark, TensorFlow, and Kubeflow, which is all in these spaces already anyway. He's a regular speaker at AI and machine learning conferences across the world, including O'Reilly, which is a big conference organization, AI and Strata, Open Data Science Conference, it's called ODSC, and GPU Technology Conference, GTC. And he was previously founder of Pipeline AI, where he worked on many AI first startups, technologies areas. And he's an expert on Kubernetes and TensorFlow, Kubeflow areas, which are the latest topics. Chris, please go ahead. Stage is yours.
Great. So can you hear me okay?
Yes, we can hear you. And when you open the presentation, I will let you know it's working before I go silent myself.
Okay.
You're ready to go.
And can you see the code and I
yes.
got some code here?
Yeah. We can see your picture and Netflix, and these I see the slides, codes as well.
Excellent.
Okay.
All right. Yeah, good to see you. Good to see the inside of your home. Yeah, everyone gets to see a glimpse into how we all live here. It's kind of fun. Okay. So let me start off. This is pretty new material, so you folks are getting kind of hot off the presses. I was actually working on this right up to the moment that I was introduced here. So, and today we're going to, for the next, I think, 30, 40 minutes, we're going to talk about quantum computing with a new service called Amazon Braket. And this is a service that's offered by my employer, Amazon Web Services. And this actually gives you access to quantum computers. So let's say it was 15 years ago and someone said, we are going to give you access to futuristic GPUs, right? We are going to let you run these machine learning algorithms on GPUs. It'll be pay as you go. So that's the feeling of excitement that I have with Braket, and this is the excitement I want you folks to feel. So let's get into, so I've got the agenda here in a sec. Let me just get through me here real quick. I think most of this was already said. So here's some links for you all if you want to check out the book. This is in the early release form right now, so you can actually go out there and I think get through the first 8 or 9 chapters. We're waiting for the big reInvent conference by Amazon. It's coming up in, I think, early December, and that's going to be virtual this year. Once all the new announcements come out, we will then launch the book early next year. So stay tuned for that. And actually, let me maximize it here. So before doing AWS, I had my own company, Pipeline AI, also worked at Netflix. So I was part of the original streaming team there. We were launching globally, so I have a lot of distributed systems experience, a lot of recommendations, a lot of machine learning, AI experience. And then, after Netflix, I was with Databricks. And so spent quite a bit of time onboarding customers and building use cases, Spark ML use cases at scale. So here's a quick agenda of the book. This is actually, if you follow that link, you could find the workshop. We're actually doing a workshop next Saturday, and this is free. We give everyone their own account for the day, so their own private Amazon account. We like tear down those accounts afterward, but these are the topics that we cover in that workshop. So we'll take data all the way from ingest through feature engineering, training, optimization, hyperparameter optimization, and then deploying. We then build a pipeline out of all of that. This particular month, this next Saturday, not this Saturday, but next Saturday, we'll be covering streams, we'll be covering multi-arm bandits, we'll be covering BERT-based kubeflow pipelines. All of this is around BERT, natural language processing. Okay, so let's talk about today's agenda. So what is quantum computing? We'll start with that. We'll talk about use cases. Everyone loves use cases, right? If you were told 15 years ago about use cases being worked on with deep learning, I think that would be very exciting. So think of this as kind of looking into the future, maybe 5 to 10 years out. Some work that's being done today to kind of lay the foundation for those use cases in the future. We'll talk about QPUs, which are essentially coprocessors similar to GPUs. We'll talk about qubits and superposition, entanglement, and of course, teleportation, which is always exciting and fun to think about. And we'll talk about how to program these QPUs, and we'll finish off with a demo showing Amazon Braket. We will actually access a quantum computer. We'll do it both with a simulator, but then also actually access a real quantum computer that's shooting the photons and doing all kinds of fun stuff. So what is quantum computing? So I have to give a lot of credit. There's this book here, which is the same one listed here, Programming Quantum Computers. You can see I've been earmarking it, pretty heavily. And I actually got this book during a conference. I was speaking, and they were giving away some books, and went and was chatting with the O'Reilly folks who I know, and just happened to see it on the shelf. So it's a very good book. It has lots of good visualizations. I've carried through some of those visualizations into this. So this presentation is a combination of some Amazon talks that have previously happened at reInvent last year when Braket was first announced. Now Braket is in GA right now as of, I believe, August 13th. It was pre-released before. It was kind of a beta release. So I've got material from this book. I've got material from a bunch of reInvents. I also, of course, have been spiraling out of control, researching everything on Wikipedia and watching things on Prime Video. Actually, quick plug for the Amazon Prime Video. There's actually lots of good quantum talks out there. Quantum. So like I said, is if 10 or 15 years ago you were trying to learn deep learning, you'd be hearing terms like convolutions and long short-term memory, and there's these obscure names. And so that's the feeling I'm getting right now with quantum, is there's all these, bell pair and the entanglement principles. And it's kind of fun because it sort of reminds me of when I was, first learning quantum mechanics back in high school, back in college. These terms are starting to surface again, similar to when I was learning linear algebra, and I didn't realize there was any use for this until many years later when, of course, deep learning and machine learning. And so these are the fundamentals. Quantum mechanics is nature's operating system. This is one of my favorite quotes, actually got from one of the Prime Video talks that I was watching. And so, this stuff dates back to the 1930s. Quantum mechanics freaked out our, friend Albert Einstein. He called quantum mechanics spooky. And he has this quote that no reasonable definition of reality could be expected to permit quantum mechanics. So Einstein, not a big believer in this. We'll see some of these surface throughout the talk. So why quantum now? There's enormous long-term potential, right? Similar to deep learning, 10, 15 years ago. We want to give folks the ability to learn quantum programming now, today. And while the applications are limited, and more sort of right now kind of geared towards the sort of HPC community, right? Like these sort of larger problems that maybe you and I don't think about. But there are quantum recommendation algorithms, there is linear regression, there is PCA, principal component analysis, support vector machines. So we're starting to see classical algorithms make their way into the quantum world. But instead of waiting 10 or 15 years, we want to give you access to these things now so that you could start programming. Very, very low level programming, by the way. Yes, as we'll see in a bit. We're building circuits. We're kind of building gates. We are like constructing circuits from gates, and it starts to get a little cryptic here and there. But yeah, so just know these are the foundations, and think of it like assembly language. Right now we are all learning the assembly language of quantum. So start like developing new algorithms, testing things out, creating your own IP, the intellectual like property. And so one thing I realized when I joined Amazon, there's this concept of the Amazon flywheel. This is something Jeff Bezos is very, very passionate about. It's a mental framework, if you will, sort of lower prices and leads to more customers leads to more choices, and this flywheel starts to continue. So similar kind of thing here. I'm calling this the quantum computing flywheel, quantum flywheel. So once we can better understand these quantum computing use cases and quantum programming constructs, we can then start to give users better experiences. We could start to build more use cases, solve them with more algorithms. Hardware developers start to get involved. Hardware capabilities then start to grow. And there's this flywheel of like more and more users, and then more and more algorithms and better hardware. All right, this is a super busy slide. This started off very simple, and then I had a lot to say here, so more and more stuff started to surface. But the high-level concept here, the high-level takeaway here is that we're in section 2 here, or quantum computing era number 2. So 1 was just trying to simulate and trying to figure out how we can simulate quantum, and we've since reached quantum supremacy, which is kind of a ridiculous term, but we just crossed just crossed this in I think late 2019, maybe October 2019, so very, very recently. And what's happening now is we can no longer track or we've sort of exceeded what classical computers can do and track. And now quantum computers have finally achieved supremacy. But we're not really at the advantage of quantum. Like, we're not fully taking full advantage of this quantum computing paradigm. We're still in this sort of noisy state, and like you'll see this this 4-letter acronym here, NISQ, which is noisy, and then we're at this sort of intermediate scale quantum era right now. So this is where we are today. Where we want to be is this era 3, which is error-corrected quantum computing. So similar to how we had to do error correction with like digital bits and like digital transistors, now we are at the point where we need to solve sort of error correcting. The problem here is, if we have 1,000 qubits, we need a percentage of those to be redundant and to handle error correction. And so we are not yet at the full capabilities of these QPUs and quantum computing. And so, like, just to give you an idea of the scale, we've been sort of hovering around 40 qubits, 30 qubits. I think there's one quantum computer now that has 72 qubits. So we're starting to approach, but really we want to be in the sort of 100,000 qubit range. And so that's where we will start to see really, really useful applications, simulations. It's provably possible. It's just a matter of hardware. cooling, yeah. Okay, so here's kind of the traditional sort of marketing slide, I like to call it, but really what we'll be doing later on is building, testing, and then running on the actual devices. We will use Jupyter, and these are just regular notebooks. There's pip install for the Python Braket SDK, and you can build your circuits and then run them on different devices from like different hardware providers. And of course, all of this gets tied into S3. It's all part of IAM security. And yes, all of the goodies from, oh, and it's pay per task. So you're not paying to actually build your own quantum computer, obviously. You are paying just for what you use, which tasks, and specify the number of qubits, that kind of thing. All right, these are the 3 providers right now. So D-Wave, IonQ, and then Rigetti. These folks have built these computers, and we are now giving access to these from Jupyter Notebooks using your like S3 data. Okay, so let's talk quickly about use cases. So of course, cryptography. This is probably one of the scarier type of use cases here, which is the ability to break RSA encryption in just 3 minutes. So if you're using traditional digital, this would take a quadrillion years, huge number of years, not going to happen within our lifetime. And suddenly we've now proven that quantum can actually factor these 2048 digit RSA keys in just a couple minutes. And the sort of history of the like Amazon Braket service is actually cryptography. So Amazon had hired cryptography experts to actually tackle this problem of quantum computers that could potentially break this encryption. And through that, they realized, oh yeah, we can make a service out of this. We're basically integrating S3, we're basically doing IAM, so why don't we just offer this up as a service? So, classic sort of AWS, they have a specific use case and start building it and then package it up as a service and then offer it to the public. One thing to note, again, classical machine learning algorithms are limited in quantum right now. So common ones, of course, that are there right now are linear regression, PCA, SVM, fast Fourier transformation, system of equations. So, pretty powerful stuff. Of course, matrices supported, vectors, superposition of these qubits, you basically represent as a vector. We'll talk about bracket notation here in a bit. That's where the service name gets its name from. It's called Amazon Braket, based on something called bracket notation, which you use to represent superposition. And so the sort of speed ups here, so there are sort of exponential speed ups happening with certain classes of these algorithms. So of course we go from ON to O log N. And if you can remember your marketing or your like interviewing days, you know that O log N is much faster than ON. And then also sort of financial, chemical, material science simulations, drug discoveries. These are what people are using quantum for today and starting to get familiar with the code and these quantum paradigms. Yeah, so logistics, drug discovery, new materials, finance. I've got a couple use cases actually coming up right next. Some like customer stories. I typically put customer stories at the end, but this particular presentation, I want to present them early because they are truly these sort of early adopters, and I think it kind of validates what's happening. I discovered this while putting this presentation together, something called the like Creative Destruction Lab. It's kind of a fun name. They help startups, and in this case is quantum machine learning startups. They've done about 20 per year. So something to take a look at. They've been using some of the AWS services, the Braket services. Okay, so here's a fun customer story here, Fidelity. So Fidelity has this group called the Center for the Applied Technology, FCAT. These folks have been using Braket to do simulations for like options pricing. They've been creating synthetic securities, sort of groups of securities that can track specific indexes and doing all kinds of simulations using hybrid classic to quantum and trying different quantum backends. So that's the benefit of using Braket, is that you're not locked into a single quantum provider. It's not just D-Wave, it's not just Rigetti, it's just not IonQ. And as more providers come along, we will start to add them. Volkswagen Group, so they've been using this. I'm a big Volkswagen fan. Yeah, so they have been using the standard interface, which is the pip install Braket Python SDK. And they've been taking advantage of the different service providers. Yes, Amgen, doing biotech drug discovery. There's a nice quote here. And let's see, chemical simulations and then material science. So they've been trying to integrate between classical algorithms and trying these out with quantum hardware. All right, let's talk a little bit about a QPU. So for all purposes, think of this as a coprocessor, like coprocessor similar to GPUs. And what's happening here, and this is kind of the incremental step, right, towards using sort of fully utilizing quantum, which is let's coordinate our actions with the CPU like we do in like GPU land. And let's just do bursts of QPU computation in this hybrid manner. So in like the upper right there, we show sort of how CPUs communicate with GPUs. GPUs do the heavy lifting of the matrix multiplies, but it's the CPU that actually updates the weights, right? If you're familiar with parameter servers in a distributed training sense, then yes, that's very similar. So you would pass the data into QPUs, put them in what's called superposition, do then these like massively parallel computations, and then you can get back those results and then continue on with your CPU operations. So QPUs are defined by number of qubits, which is the short name for quantum bits. And then, like I said earlier, today's quantum computers have less than like 100 qubits. We're striving for thousands and tens of thousands of qubits, but we need cooling, we need perfect vacuums, we need all kinds of, very sophisticated hardware to do this. And then, like I said earlier too, some of these qubits, so while we have 72 qubits, a certain percentage of those are needed to provide redundancy for error correction, right? There's noise, it's called decoherence. There's noise that's happening, just, if there's any slight perturbations of like the environment, this could cause these photons to not shoot like properly. All right, so qubit, short for quantum bit. There's also Q nibbles, if you remember back in the day, 4 qubits or 4 bits was called a nibble in digital land. So 4 qubits is called Q nibble. And of course, 8 qubits is Q byte. And this is a picture. I was at the San Francisco Gay Pride Parade, I think it was last June. And I saw I think it was Facebook. So they were actually giving out these T-shirts that said qubits are not binary, and it was, yeah. So that was the picture I got there. But yeah, so pretty funny. And so qubits. The sort of interesting thing is qubits will ultimately end up in zeros and ones, just like digital bits. And I want to just fast forward to that concept, because while most people talk about how these qubits can be in multiple positions at the same time, really at the end of the day, it's a photon that's being shot typically, and that photon's going to end up as a 0 or a 1. It's just probabilistically in both of those states at the same time. So until you actually read the qubit, which you will always get back 0 or 1, it is probabilistically in one of those states. So if it's 73% 0, 20% 1, And I'll kind of fast forward to the sort of answer key with quantum, which is what we're doing is constantly manipulating these percentages and these probabilities, and doing things like phase manipulation, right, like the entanglements. Yes, all of these concepts, what we're trying to do is bump those percentages up. So that when we actually do the read, we will probabilistically with high probability, with like high confidence, get the value 0 or 1. But if you think of qubits as zeros and ones, you are not that far off, right? At the end of the day, that's what we need, zeros and ones. It's just the ability to manipulate these things in massively parallel, like using nature's operating system without limitation, and but then we are ultimately pulling these in as zeros or ones. So read forces that like qubit value to become 0 or 1. And when you read, you are destroying the quantumness. So no longer is there probabilistic, it will go to 0 or 1, and with that particular confidence. So probabilistic state is called superposition. So let's talk about that for a sec. So so the analogy I like is when you roll dice, you're really putting those dice into sort of a logical superposition. The value of the dice as they're rolling is probabilistic until we decide as humans to read that value. And we just happen to read that value when those dice stop rolling, right? But that's not when we need to read that value. I could read that value as it's, picture, I have a video camera, I'm recording, and I stop the frame. I could choose at that point to actually read those values. And superposition is represented in what's called circle notation typically. This quantum book uses circle notation very heavily. And what we see here with the circle notation is there's this sort of magnitude, which is the radius. It's kind of the bluish or sort of grayish area. And then there's angle, okay? And on the right side, we see the first two are not in superposition, right? They're fixed, 0 or 1. So there's the bracket notation. When we put data into superposition, these qubits into superposition, we now have two numbers, right? And so 0.70 and 0.70, that actually normalizes to 50%, 50%. And we see, well, it's not really clear those are 50%, that like radius, the sort of area within is 50%. So we are always normalizing these, so 0.7 is 50-50, 0.95, 0.31, I think ends up being 73% maybe, and 27%, and then that very last one, 50-50. Okay, so, and then once again, this is the probability that we will read a 1, okay? So here's more about circle notation, a couple different forms of it. One thing to note is there are going to be 2 to the n circles, number of circles. And n is the number of qubits. So if we have 1 qubit, 2 values, 3 qubit, 2 to the 3 is 8. If we do 2 to the 10, that is 1024. If we do 2 to the 32, now we have, what is that, 4 billion? If we get to 300 qubits, that's actually more circles than total number of atoms in the visible universe. So this is where, let's see, I have a slide on the amount of memory needed here, but yeah, we'll talk about that, I think, in 1 or 2 slides. So sort of on average, qubits needed for these specific use cases. So cryptography, the one we were talking about before, where we could actually break RSA, takes about 6,000 qubits. Now keep in mind that these are perfect qubits. These are without noise, without decoherence, without the error correction. So to achieve 6,000 clean qubits, right, like we actually need 1 million error correcting sort of redundant qubits. So qubits today, so we are okay for a little bit. And we won't be able to actually break these like 2048 keys until we can either get these cleaner qubits, or we just have a super large million sort of error correcting redundant qubits. And so chemical simulations about 200 qubits. Typical optimization problems that are commonly found with machine learning and deep learning, 100 qubits. And then classic sort of simulations for material science, we're seeing those come in around 70 qubits, which is actually at the high end of the like modern like quantum computers. Okay, so superposition, back to this real quick. So we actually measure superposition in something called amplitude. And yes, amplitude is actually magnitude, which is that radius, plus the relative phase. And that's the 360-degree angle. And I say relative phase because what we're doing is, between 0 and 1, there's actually relative angle difference. And so pretty much all of quantum programming involves phase manipulation and sort of amplitude. It's called the amplification. And right, so we are using nature to actually perform these calculations, which is pretty cool. So the first thing that we do typically is put our conventional data, this is called a write, into superposition. So first there's a write, and there's this had gate, and I'll use the term gate and then operation sort of interchangeably. They're the same thing. And so we would first write the data and then put it into superposition with had, which is short for how to, I think it's Hadamard. I should probably have that in there because it's a very important concept. This right here, this simple circuit is a quantum random number generator. And if you're familiar with digital random or sort of pseudo random number generators, through like classic programming, right? Like we know that this is not really random, whereas this is nature random. And there's a company called Cambridge Quantum Computing that actually just released a paper yesterday talking about how they can guarantee, because in some cases, we are not guaranteed randomness, but they have a way to actually guarantee randomness. And of course, with machine learning, with like deep learning, we actually celebrate randomness, right? Like, so being random is good, and being truly like quantum random is super powerful. So let's talk about the entanglement. Something called Bell pair. This is John Bell, famous Northern Ireland physicist from the like Belfast area. The like concept here, and this is super critical to all quantum programming here, is that when you read one qubit, we can actually have another qubit that forces itself to go to the same value. So we would entangle qubit A and qubit B, and when we read qubit A, that's forced to go to 0 or 1, and B then, which could be 700 miles away, could also or will also flip to 1 or 0. I can't remember which one I used, but basically they will mirror the values of each other. And this is the part Einstein was not comfortable with. He said this is spooky action at a distance. He just like would not believe it. Part of it is it appears to be faster than the speed of light, which he like did not believe existed. So also keep in mind too that we can extend this entanglement to beyond just 2 like qubits, but yes, we can extend this to multiple qubit groups. So of course, back to these q nibbles of 4 qubits and q bytes of 8. This is a fun topic, teleportation. It's not the true teleportation. If you see down at the very bottom, just to kind of, this is a bit of a sort of anticlimactic slide here, but it's not true matter teleportation. We are teleporting the state of one qubit, and the state of a qubit is its magnitude and its like relative angle. But think of it like a quantum Ethernet cable, right? We are able to communicate and pass information. Very, very powerful for cryptography. The classic Alice and Bob sharing information in a like secure way. And then of course figuring out if there's a middleman that's involved. And so yeah, we'll actually show. I have a Jupyter notebook that is using Braket, and we will actually run this on a quantum computer. So again, when you transport the state from qubit A to qubit B, that actually destroys qubit A. If it was copying, so copy does not exist in quantum land. If copy did exist, we would have a very different civilization than we do right now. So quantum A to quantum B, that will then destroy the qubit A. Yeah, qubit A to qubit B. We can only currently transport or teleport over short distances, and typically just small. So the order of like millimeters here. Yeah, and the longest teleportation that I could find as of today is 1,400 kilometers, or about 870 miles. But typically these are happening just within the actual QPU itself. Okay, and let's talk about simulators. Now, this isn't the use case of a simulation. This is actually quantum computing simulator. So this is one way to test out in a cost-efficient manner your quantum programs. The problem here is we can only go up to about 34 qubits before representing the state will require so much RAM, right? So this is what I was saying earlier. If I back up a few slides and had those numbers here. 32 qubits requires a fair amount of circles. And so let's go back here. I think I actually have got the. So 30 qubits requires 16 gigabytes of RAM, and so that's what's happening here. This simulator, in order to represent those circles and the state of 34 qubits, we actually need 16 gigabits of RAM. And this goes up with every 10, this goes up. So 40 qubits, 16 terabytes, 50 qubits, 16 petabytes. And so trying to simulate beyond 30, 40, 50 starts to get out of classical computing constraints. One option is the simulator. Of course, then there's also D-Wave, Rigetti, and then IonQ. All right, and so this is what we will be doing here. We have a managed Jupyter Lab environment that's just like SageMaker notebooks, and we will actually test our circuits, and then we will then run this. So the hybrid quantum algorithm piece is the fact that we're using CPU for some stuff and then QPU for other stuff. And so the cool thing here is that the data can be pulled from the Amazon S3 service. It can also then, when tasks come back, we can actually notify and register CloudWatch events. We have full logs for these tasks get logged into CloudWatch. So this is where the benefit starts to come from, is you don't have to change too much from your current workflows to actually launch these quantum tasks. All right, so here's an example. We're doing the entanglement here. So the upper right diagram there shows the first step is to get data into superposition. So similar to when you want to get your data into a GPU, and GPUs massively parallelize and operate on batches of data and have thousands of cores and have a different paradigm than CPUs. The equivalent with quantum is superposition. So you have to get your data into what this hardware can optimize for. So this is what we're doing. We create the circuit, we then put the data into superposition, we entangle these qubits, and then we actually run the task. And here I'm saying do 100,000 shots. Now, this is a current like limitation of quantum computers right now, which is the more shots you do, think of it like a photon being shot, the closer you get to the real number, or the like actual, the true probabilities, right? So if we do 100,000, we would get 50,000 back in one state, and then 49.9, yeah, so roughly 50,000 in the zero state. And so this is, some of the gate logic here. The had, which is what that H is, that's the first thing that we do on qubit A, and then qubit B we entangle, and that's the symbol for the entanglement. All right, and then doing the same thing here for teleportation. So this is where we start to do the phase manipulation, and basically we are like always writing data into the QPU, the like qubit registers that then we then put them into superposition, gets them ready to be operated on by the quantum computer. Entanglement using C naughts. These are the gate names, or like the sort of lower level operation names. Phase is very important. That's what's going to change the angle, change 45 degrees, 90 degrees, 180, and then we will ultimately read the data from the QPU back into CPU. So I'll show you. See, how much time do we have here?
We have. I was asking you to wrap up.
Oh, were you?
If you have, we are already getting there, and then there may be some Q&A. There's no Q&A yet. People start asking questions after you finish the talk sometimes, and you probably want to wrap up. You're not that just there. You probably can take a minute or two.
Okay. Yeah, just have these two. I'll just show quickly, and then a couple wrap-up slides. Okay, so here we're just setting up the S3 bucket. We're going to create this circuit. So this is just creating the entangled bell pair. Here I ran it both on the simulator, which is just a software simulator running on a classic computer, but then I changed it to then actually run it on the IonQ device. So there, printed it out. Here's the circuit, same thing I did on the slide. This is kind of fun. It's like ASCII quantum circuits. It's kind of fun. It's not a very, it's not the most readable, but it's good enough. Qubit 0, qubit 1. Okay, and we then run. We provide the number of shots. That could be 100,000. And we get back the results. So let me show you the actual tasks. If we clicked on that, it would take us here. And these are the tasks. So you can see I ran two. I've got one that's queued up. So think of this like, back in the old days when you would submit jobs in the computer lab and have to wait, maybe a half a day for the job to actually execute. So very, very similar feeling, but I was able to get in 2 or 3 in here before. There's a slight UI bug there where it always says it's not available. Let's get it again. So there's our status, shows us where the actual output went for this. So I can click on this bucket, and I could open, I can download this and see the results. And so like you could see this being part of your more complete pipeline here. So there's the results. It's the same results that I had printed out, but it shows you the instructions that were run, the gates, the circuits. And then here's teleportation. So we're using super dense coding as kind of the quantum term for it, setting up the bucket, creating the circuit. There's a printout of our circuit. We're then running it on a device. You can view the tasks and then also look at the results and plot them with Matplotlib. Okay, so that's the demo. By the way, all of this is in the GitHub repo that I'll show here in a sec. So looking ahead, quantum research is actually improving conventional machine learning algorithms. So pretty cool paper here, quantum inspired classical algorithm for recommendation systems. We've got error correcting qubits. That's a hardware feature that was like deep learning was 10 to 15 years ago, and limited by hardware availability. But we are making that better with Braket. So real quick, so there's an AWS Center for Quantum Computing opening in 2021. It's a partnership with Caltech. So it'll be on that campus, near the campus. There's also the Amazon Quantum Solutions Lab, which is experts that we have that you can work backwards from your use case. So, start with your use case and then back in and figure out which parts are best for deep learning, which parts are best for the quantum, doing benchmarks and then analyzing results. Some technology partners, and that's it. So check out our book, the GitHub repo there. If you also go to that main website, Data Science on aws.com, that will, so that has links to all of our content. These notebooks are all in there.
Thank you, Chris. I know you are a wealth of resource. For every time you come, you have a lot of information, and you deserve an hour and a half to probably half a day or a full day to be able to speak everything that you already know. And quantum computing, it's a very exciting field. I encourage all of you to delve into it. And I'm doing a full day conference. We can talk about